So where I'd left it off before is that in the most general case of electromagnetism, where both kinds of fields are present, the force on a charged particle would equal Q times E plus V cross B. That's probably the last thing in your notes. The equations that we had earlier for electric force and for magnetic force would follow from that as special cases. So, just for an example, let's say we have this positively charged particle, proton apparently, it's shooting through a magnetic field, which is perpendicular to the page, and the question is, what would the electric field need to be if the proton is to keep a constant velocity? This kind of arrangement can be used to create a beam of charged particles, whether they're electrons or ions or whatever kind of particle beam you're talking about. If you want to create a beam where they're all going exactly the same speed, you shoot it through a situation similar to this. And you see the ones that are going too fast will curve off to one side, and the ones that are going too slow will curve off to the other side, because in the one case the magnetic force is bigger, and in the other case the electric force is bigger, because the magnetic force depends on the speed. The ones that have the speed you want go straight, and that's how you can accomplish that. Anyhow, 7-3. Thinking back well into the earlier part of the fall semester, if something's going to have a constant velocity, that means there's no net force on it, okay? Newton's second law. Constant velocity means no acceleration. If A is 0, the net force is 0. So what this problem wants us to do is set the F in the Lorentz force equation equal to 0 and solve for E. So we've got F equals that. Force is equal to 0. I could look up the force or the charge on a proton and fill it in for Q, but why bother? If you divide both sides by Q, it's gone. Doesn't matter what the charge is, the answer will be the same. And so if you subtract the V cross B from both sides, in order for the electric and magnetic forces to have opposite directions so that they'll cancel each other out, E and V cross B have to have opposite directions and opposite magnitudes for that matter. So the velocity vector is written right there. Well, both of them are written right there on the picture. Just copy them into the formula. Need a little more space than that. Minus sign cancels the minus sign. As far as evaluating that, there's basically two separate things going on side by side. You have to, do you need a copy of the handout?
I can read.
You ready for it? Okay.
Thank you.
There's two things going on. There are some numbers to multiply, and there are some vectors to multiply. So the 7.6 million times the 0.0026, they equal 19,500. And that has to be multiplied by I cross K. Well, there are several ways of figuring out that I cross K is equal to negative J. You could draw some kind of a picture and then start applying the right-hand rule. Or you could set up the 3x3 determinant like I showed you with that other problem a while ago. But for a problem where each vector has only one component, that procedure involving the 3x3 determinant is kind of, it's kind of like shooting flies with an elephant gun. It's really more powerful than what you actually need. There's, you see people do this sometimes. They just make a little diagram. Little circle with I, J, and K written next to it. And you take your finger and you just go hopping around on it. In this particular case, so I is the first vector. You start on I. I cross K, and you end up on J. And you went around the circle in the negative direction. So I drew this arrow counterclockwise. That's positive. If you go around backwards, it's negative J. Okay. Any of the unit vectors crossed with themselves or crossed with another unit vector, or well, the basis vectors anyhow, I, J, and K. You can figure out off that little diagram. It's like K cross J would be I. I don't have the camera pointing at this. This is probably not a good idea. Better do it over again. So this one here is I cross K is J, except you want against the arrow. You want clockwise, which is negative, and so it's negative J. K cross I would be positive J, because you went around this way. I cross K is negative J, because you went around that way. Or for any other combination, K cross J would be negative I, and so on and so on. Hopefully you see how that works. So for a problem like this one, where there's only one component to each vector, and it's right along, they're each right along one of the coordinate axes, that's probably the easiest way to figure out the cross products. Any vector crossed with itself is zero, because there's a sine theta factor. Cross product of two vectors is magnitude of the first, magnitude of the second, times the sine of the angle between them. Well, if a vector is crossed with itself, it makes a 0-degree angle with itself. And so something like I cross I or J cross J, any of those would be zero. When you cross them with each other, you can figure it out off of that thing. Well, there are certainly some situations where you have to consider a charged particle moving through empty space, whether you're talking about an electron beam in a vacuum tube or ions moving around in the sun, or it comes up. But the most important applications well, I guess it depends on what's important to you personally, but for our technological society anyhow, what would be the most important applications are when the moving charges are inside of a wire rather than just moving through empty space. Unlike electric fields, yeah, I've got this wire drawn here in the middle of the page. Maybe I should do this. You got a wire with an electric current flowing through it. Unlike an electric field, magnetic fields easily penetrate the metal. Okay, they just pass right through it. So these charged particles that I drew inside this wire, moving to the right with some speed v, exactly the same thing happens to them as if they were moving through a magnetic field in empty space. They feel this QV cross B force, just like the particles in this problem that I just ran through. The only difference, well, typically you'd be talking about a metal wire, so the particles would actually be electrons. They'd be negative and going in the other direction. Minor difference. Point is, the electrons are not free to move to, are not free to leave the wire. So if the electrons get pushed to the side by the V cross B force, the wire that they're in gets dragged to the side along with them. So there's a force on a current carrying wire in a magnetic field. And this is important because, well, for example, how many of you have ever heard of a device called an electric motor? Yeah, you didn't actually have to put your hands up, but I figured I already knew the answer. But that's what makes a motor go around. There are other applications. So if you have a current carrying wire, you could calculate the force on it from Q times V cross B, where Q is the charge of the little particles moving through the wire. But that's kind of cumbersome. You have this ridiculously large number of ridiculously small particles that you can't even see. And for their velocity, you know, you can't directly measure that. There's ways of inferring it, but wouldn't it be handy if we could modify the formula so that it involved stuff that's easy to measure, like how many amps are flowing through the wire and how long the wire is and that sort of thing. So, well, what this is leading up to is I'm going to say that the QV cross B force on that wire is equal to I times L cross B. But a little bit of background before I actually get to the thing with a box around it. I'm going to define a length vector, which works out better if you're writing than if you're typing because they all looks like a 1 and nobody knows if it's a letter or a number. But the vector has a magnitude and direction. For its magnitude, it's the length of the wire. The wire in that picture is 30 centimeters long. Magnitude of this vector would be 0.3 of a meter. For its direction, the direction is the direction that positive charge is moving inside that wire. Or maybe a better way to say it is the direction of the drift velocity of positive charges in there. In other words, the direction of the current, except I'm not supposed to say the direction of the current because technically current is a scalar. Current is charge per unit time. Charge is a scalar, time is a scalar, scalar divided by a scalar is a scalar. That's the thinking behind that. I'm not sure how giving the length of the wire a direction makes any more sense than talking about the direction of the current, but well, as maybe you've heard me say before, nobody asked me before they set all this stuff up. Possibly because I wasn't even born yet, but we're going to draw a picture. Here's the wire. There's the length vector. This wire is presumably part of some larger circuit. I mean, in this diagram in the notes over here, you don't have charge mysteriously appearing out of nowhere at one end of the wire and mysteriously disappearing at the other end. It's got to be part of some larger circuit. It's just for some reason you're interested in this particular section of wire here, and L is its length. So, having defined that, force on a current carrying wire is I times L cross B. If I was emperor of the universe, it would be L times I cross B, because it seems to me like the current is something that has a direction, but, well, I'm not emperor of the universe, so we have to play the game the way it's been set up. And,
Why does the current not have a direction, but length does?
well, that's what I'm saying, you know, it's like, I'm not sure one way of doing it makes any more sense than the other way of doing it. But this is what has become traditional. This is what all of the textbooks say. So that's what I'm going to say too. Because
That'll be your first thing to change. Make current.
I thought we already talked about this. The first thing is tooth decay. We got to get rid of that first. Lower back problems, I think, are fairly far up the list also. But
Change current to be a vector and be a scalar.
yeah, after we take care of those medical issues, and eventually we'll work our way down to this thing. As far as seeing that this is equivalent to QV cross B, well, current by definition is charge over time, or at least if it's a steady, unchanging current, it is. If you've got some sort of changing current, you have to use infinitesimals, dq, the derivative charge with respect to time. But for the simplest case, if it's a steady current, q over t, and then the charge moves the length of the wire in a time t, distance over time is speed, so q times v cross b. I'm kind of summarizing what a more rigorous derivation would look like, but just to give you the idea that you take q v cross b, you manipulate it around for a few lines, and you can show it's equal to I times L cross B. And this is more convenient than talking about the forces on the individual electrons inside the wire. So a little more practice with the right-hand rule, because I probably can't spend too much, well, aside from the fact that the semester contains a finite amount of time, I probably can't spend too much time on that. So number 4. Part A. Like I said, you can think of this in terms of the right-hand rule, or you can think of it in terms of this little circular diagram. Well, let's look at it both ways. In terms of the right-hand rule, you've got, well, maybe I should tell you the answers first. Part A, the answer is the negative z direction. And part B, the answer is the negative x direction. So hopefully you got that. Part A, the magnetic field is pointing toward the right, positive x. And the direction of the current, oh, did I say that? The direction of the length vector, I mean, is up the y-axis, like that. So you get out your right hand. Well, first of all, it's got to be perpendicular to both of these vectors. So before you do anything with your right hand, it's either plus z or minus z, okay? As for which one of those it is, you wrap your fingers around the z-axis, pointing from the first vector toward the second one. L cross B, my thumb is pointing into the blackboard. So fingers wrap around in this direction, and my thumb points in the negative z direction. Or, if you prefer to look at it this way, magnetic field points in the x direction. The length vector points in the y direction. So L cross B, start here. J cross I is negative K, okay? L cross B points in the negative Z direction, negative because I went around in the negative direction, clockwise. And then part B is a similar kind of thing. So this time, the wire is perpendicular to the page, and in the middle of that wire, I put a little dot indicating the current flows out toward you. So the length vector is in the positive Z direction. Magnetic field is in the Y direction. So this might be one of those cases where it's kind of handy to make the little model out of pens and pencils. Okay, if you have a good pencil, I got a short one here. Length vector sticks out that way. The B vector points up that way. And of course, you don't have to worry about, you know, the direction, the current is by definition positive, okay? So it's not like you have to worry with QV cross B, where you have to remember if it's negative to turn the direction around the other way. That doesn't come up with IL cross B because I by definition, I by definition has no direction, but it's in the direction of the flow of positive charge flow. The length vector is. Anyhow, L cross B points to the left. So you could get the answer that way from the right-hand rule. Your thumb ends up pointing in this direction. Or jumping around the little circle, magnetic field points in the j direction, and the length vector points in the k direction. So L cross B, that would be k cross j equals minus I. So minus I or minus x, whatever you want to call it. That's the direction of the force on that wire. And then number 5 is something kind of similar, except I threw in some numbers to go along with it. So maybe an electric power line is not the best possible example for this sort of thing, just because when I get to the answer, you'll see it comes out really small. Magnetic forces, well, first of all, power lines carry an alternating current anyhow. So the force is constantly switching direction back and forth and averages out to nothing. But even if you had a direct current of that many amps, the Earth's field's not terribly strong and the force comes out pretty small. Nothing to worry about compared to what, wind and ice and things like that can do to power lines. But as a little exercise, line carries 50 amps. And 65 meters, maybe that's the section of wire from one pole to the next. Sounds about right. We've got 65 meters for the magnitude of the length vector, and it says that the current is in the positive x direction, which is actually not the direction of the current at all. As you can tell, I find this very awkward to talk about it this way, but I should probably stop that. I'm being a bad role model. It says the Earth's field is 6/10 of a Gauss. Remember, it's the Tesla, which is the SI unit for a magnetic field. Tesla's is what's going to make the force come out in newtons, not Gauss's. There are 10,000 Gausses to the Tesla. So 0.6 times 10 to the negative 4. In other words, 6 times 10 to the negative 5. For its direction, it says down the z-axis. So that would be negative k. You don't necessarily have to have all your coordinate directions, horizontal and vertical and so on. In this room here, the Earth's magnetic field points at an angle kind of like that. Well, let's just, for convenience, say that that direction is the z-axis. No law that says it has to be vertical. So the force, sliding over to the middle of the blackboard, force on this wire is I times L cross B. Fill in those 3 things I just wrote down and evaluate. I equals 50. L equals 65I. B equals that. And just like the other example that I did 20 or 25 minutes ago, once again, there are basically two multiplications to perform here. You have some numbers to multiply, and you have some vectors to multiply. So for the numbers, 50 times 65 times 6 times 10 to the negative fifth. There's a minus sign in there also. Told you the force wasn't very big. I cross K. Start out here on the I cross K, you land on the J, and you went around the negative direction, and so it's negative J. Minus cancels minus. And don't forget the unit that it's measured in. It's the force in newtons. Or instead of the little circle, make a sketch of the situation. Do the thing with your right hand. So that, or the right hand rule. Whichever is your favorite. Page 22 says, torque. Yep. Because a few minutes ago I was talking about motors. What you have inside of a motor is not long straight wires like you have slung between electric poles. Rather, you've got some wire that's been, well, yeah, kind of like that thing that you're lovingly caressing right there on the end of your teeth. No, kind of. Yeah, kind of. Yeah.
I know.
I really should have brought a camera because that's actually kind of the picture.
This is what the first telephone looked like.
Anyhow, in a motor, you have coils, you have windings, you don't have straight wires, and you're actually trying to produce rotary motion. You're trying to create torque, whether it's make the grinding wheels go around on a bench grinder, or make the wheels go around on some kind of electric vehicle, or whatever. You're quite often, I mean, there are motors that produce back and forth motion instead of round and round, but most of them are producers of torque. So I'm going to kind of summarize the details because, you know, there's a limited amount of time and you probably would rather I didn't get too deep into the details anyhow. But I drew a rectangular loop there, even though coils more often are round, because this would be the simplest case to deal with mathematically. Each of the four sides of that loop, I should point this over here again. Each of the four sides of that loop are examples of the straight wire that I was talking about back here. Each of the four sides experiences a force equal to I times L cross B. If you do the right-hand rule, or whatever is your favorite method for figuring out the direction, you will find that the force on the top of the loop is up and the force on the bottom of the loop is down, so they cancel each other. There's no net effect. The force on the left-hand side that I call F1 points out toward you, and the force on the right-hand side points away from you. And so there is no net force from them, but they produce a torque, because if you're looking at it from above, it's like, here's the loop of wire, and there's the axis of rotation, and you've got F2 going that way and F1 going that way. So there's no net force, so the loop of wire isn't going to shoot off to the side and go someplace like that, but it will twist until these two forces become collinear, and then that would be the equilibrium position for the thing. So as long as I've got my camera aimed over here, I'll do my writing at this end of the board, I guess. Just to summarize, what I could make 5 or 10 minutes longer if I wanted to cover all the details. From Physics 131, torque is equal to R cross F. Basically, if you're trying to turn a bolt while you're working on a car, how long is the wrench times how hard are you pulling on it? Force times leverage. In more sophisticated notation, R cross F. R is the radius vector, F is the force. Well, the force on either one of those wires, F1 or F2, either of them, is given by that formula I was talking about earlier today. I is equal to L cross B, capital B for the magnetic field. Using lowercase letters, I said that the dimensions of this rectangular loop were A and little b for length and width. So if you're calculating F1, the length of that wire is the lowercase b. Same thing for F2. Other side of the loop is the same length. So that goes in for L, for the magnitude of L. As for the radius, the magnitude of the radius vector, well, the axis of rotation goes down the middle of this thing. If you think of it as dangling from a thread so it's free to rotate, the thread is the axis of rotation right in the middle. From that axis out to either wire 1 or wire 2 would be 1/2 of A. So you use R cross F to calculate the torque on wire number 1, and also to calculate the torque on wire number 2, and you add them together to get the total torque on the entire loop. And this is the part where I'm going to kind of summarize. So it would be R cross F for the one wire plus R cross F for the other wire. When you do the multiplication, you've got an A from here that went into the radius, and you've got a B over here that went into the length of the wire. A times B, length times width. That's the area enclosed within the loop. So when the smoke clears, The B just carries down without anything happening to it. A times B, as I said, gives you the area, capital A. And the I kind of carries through without anything happening to it either. And you've got I times A cross B, where A is the area vector as illustrated in the little picture there. Well, I've talked about area vectors before when I was talking about Gauss's law. If you have, if this is my rectangular area that I'm talking about, its area vector is perpendicular to the plane containing the area, like that. Now, just saying it's perpendicular is not quite specific enough. That could mean this way, or it could mean the other way. How do you choose between those? Should probably come as no surprise. It's right-handed, okay? Whatever direction the current is flowing around the edge of this, flowing around the loop of wire, you grab the loop of wire with your fingers pointing in the direction that the current flows. So, like looking down at this from above, if the current is going around counterclockwise like that, I get my fingers pointing counterclockwise. My thumb points in the direction of the area vector. If the current was going around clockwise instead, of course, that'd be counterclockwise if I was under here, but looking down from up here, if it's going around that way, and I think I put a little picture like that on your formula sheet too. So the area vector is perpendicular to the area bounded by the loop of wire, and the direction that it points is right-handed. One more substitution before we get to the part with the box around it. The quantity I times A. The current in that loop of wire times the area enclosed within the loop of wire. It's called its magnetic moment. So let's define the magnetic moment, which in most textbooks is represented by the Greek letter mu. Current times that area vector. So like it says in the pre-printed notes, the magnetic moment and the area vector would have the same direction because I is just a scalar, and so it doesn't affect the direction any. Substituting that in what I wrote a moment ago, the torque is mu cross B. Well, there's a good reason they don't use Omicron. It looks too much like a zero. And then there's Xi. I mean, no, that's wrong. I still am no good at that one. It's just too hard. The guy I went to college with just called it squiggle.
Actually, my dad's professor called it twiddle.
Twiddle?
Yes.
Now this was the same guy that came up with the Zot operator, which is very useful for the symbol for the Zot operator. I wonder whatever happened to him. I haven't seen him for 40 years. But the symbol is a little cloud with a lightning bolt coming out of it. And what it does is it multiplies both sides of the equation by 0 and then adds the correct answer.
capital version of U is just an M.
Yeah, that would be boring.
The one that you're talking about, it doesn't look that bad. Hey, I'm looking at the right one.
If I don't go off on too many more tangents, I've got enough time to run through this example. So we have a coil here that looks an awful lot like the coil on the end of the table. And it says it has 300 turns. Actually, I think that one has 570 if anybody cares. But don't feel like counting. It tells the current. So I want the magnitude and direction of the torque vector because this coil is in a magnetic field that points down and to the right like it shows in the picture there. So part A. We'll get to the direction when I get to part B. For now, I'm just trying to get the absolute value of I times A times B. So the area, first of all. See, you can hear the ocean, right? People sometimes, they see a cylinder like that and they go, oh, I have to calculate the surface area of the cylinder. And they say 2 pi r times length, and that's wrong, okay? A is the area enclosed within each loop, okay? You got a loop of wire around the edge, and how much area is inside of that? In other words, it would be the cross-sectional area of the coil, not its surface area. So pi r squared. 0.07 of a meter, calls that the effective radius because, you know, when you've got hundreds of loops like that, some of them are wound on top of others, and so some loops have a little bit bigger radius than some of the others do. This is what it averages out to, is what I'm saying. And so we've got an area of 0.0154 of a meter. And once again, I'm written a little too far over to the right. If that's the area, then the magnetic moment would be that number. Well, actually, the magnetic moment of a single loop would be I times A. But if there's 300 loops, the magnetic moment would be 300 times that. You have to add up the magnetic moment of each of the 300 loops, and the total is N times IA. .300 turns, 2.5 amps, 0.0154 of a square meter for the area. The magnetic moment would have units of current times area, amps times square meters. The number of loops, the 300 is just a dimensionless number. And then the magnitude of the torque, we'll get to the direction in part B. Right now it's just asking how big is this torque. The magnitude of a cross product is the magnitude of the one vector times the magnitude of the other vector times the sine of the angle in between. Just for what does this all mean? Basically, mu is how strong of a magnet is the coil, and B is how strong is the magnetic field that that coil's been placed in. So how strong of a magnet is the coil? How strong is the external field? And those two things together with the angle between them is what determines the torque on the thing. Anyhow, the magnetic moment, 11.55. For strength of the field, I was given in the question. It's labeled, it's not terribly legible on the wall there. Hopefully it came out a little better in the copy that's in front of you, but it's labeled on the diagram, 0.15 of a Tesla for the field. And the sign, well, it's supposed to be the angle between mu and v. Now, it shows here. The area vector, oh, I'm out of my camera again. Need a full-time camera person. Like it shows in the picture, the magnetic moment vector is along, here it's a loop, it's along the axis of the loop. The coil, well, it's along the axis of the coil. So if you got this thing here, the magnetic moment is right along its axis. Just picture an arrow going right up the middle of this coil. Right-handed. If the current's going around that way, then the field is in that direction. If the current goes around the other way, then mu points that way. Anyhow, time to wrap this up. The magnetic moment is in the x direction, and the field points, okay, that's 60 degrees is the right angle then. That's the correct angle to put in for theta, because that's the angle between the horizontal, which is the direction of the magnetic moment, and the direction of the field vector. Always want to stop and think about things like that, because sometimes I give you some other angle and make you figure it out. One and a half Newton meters is the magnitude of the torque. As for the direction, magnetic moment, like I just got done saying, is that way. Along the axis of the coil, right-handed. E is like that. So, mu cross B, get your right hand out, mu cross B points into the blackboard in the negative Z direction. So here's a picture of the torque vector. It's an X. It's an arrow pointing away from you. The Greek letter tau next to it to label it as the torque vector. If you remember back to Physics 131, a torque vector pointing in the negative Z direction creates a clockwise torque. So if there isn't anything to hold it back, this thing will start to turn that way. And I've just made back all the time that I lost by letting you go early last time. See you Friday.